Last time, I was saying last time, like raise your hand if you've ever sorted anything before. Of course you have. Everyone has. You've sorted things. You know, we started talking about searching. Searching was our first like general purpose algorithm. And you know, you might think like searching, well that's kind of trivial, right? But of course, you know, the reason we like searching, there's a couple reasons we like searching. One of the reasons is you all understand the problem. Like it's like obviously you know what searching is. But you've never probably really thought about the algorithm you followed whenever you searched something. And so we took the time to talk about a linear search, and we kind of analyzed it. But then we saw an alternative search, binary search, which had a catch. The data had to be sorted. But if it was sorted, you could do binary search, which was way better than linear search. Way better. Not even like hilariously better. And even though you all kind of intuitively knew what that search was, like you've all flipped to pages in a book before, you've all looked through something like a phone book, let's say, where you've been able to kind of like take chunks out of the search at a time instead of one thing. And again, you knew you knew these algorithms without really thinking about them. So now you're thinking about, now we're going to talk about sorting. And again, sorting is obviously something you're familiar with. You've all sorted something. So it's a problem you're really familiar with. And you're going to think like, well, it's trivial. Well, we're spending all this time talking about sorting. But the point of talking about sorting isn't so much sorting. Obviously, that's part of it. You learn about sorting algorithms, fine. But the reason we like to talk about sorting is because it's sufficiently difficult where your algorithms have to become a little bit more interesting. You've all done it before. You all understand the problem. And there's a lot. There are several intuitive ways people sort things. Like in a moment, I'm going to ask people like how you've sorted things. I'm going to ask you to think to yourselves, talk to your neighbors about how you sorted things before. If I gave you a stack of exams and said sort them, if I gave you a pile of numbers and said sort them, what would you physically do to sort them? And chances are we're going to get 2 or 3 distinct algorithms. So it gives us a chance to explore how like it's you know, there's a problem. It's the problem of sorting, but various algorithms. And again, how many ways are there to sort things, do you think? Yeah, of course, there is. A lot of them are going to be garbage, but there's actually a lot of common intuitive ones. But you'll think, like, for how many millennia do you think humans have been sorting things? Probably a long time, right? People have probably been capable of sorting things for millions of years, right? Whether it was rocks by sizes, I don't know, a bunch of cave people sorting rocks, I don't know. But they were sorting things. But the joke of all this is you think sorting, it's a trivial problem. But it wasn't until like 100-ish years ago, I don't even think that long, where someone realized like, wait a minute, we all suck at sorting. We're all going about doing this the wrong way. There's way better ways to sort things. But they're not as intuitive. They're not as natural to you to think of. They're not overly complex. They're absolutely something we're going to learn next semester, and you are more than capable of understanding them. But when I'm about to ask you how you're going to sort things, I'm willing to bet you're not going to say one of those things unless you're full of shit and you're lying, and you're saying you know this one that you didn't really ever do because no one would. So a big part of this is it's not so much sorting. It's a well-understood problem. We could approach from different ways. And it seems trivial, but when you get clever about it, you can come up with a way better way to sort things. And of course, it gives us a chance to, because it's a well-understood problem, it gives us a chance to really think about the algorithms and how much work they take and whatnot as well. So I'm going to give you a few minutes to think to yourselves, talk amongst yourselves if you're sitting by someone, maybe move close to someone, and think, what are the steps you do to sort things? Try to, like, you've obviously, if you've sorted something, you've followed some sort of algorithm, if not some weird bastardization of some algorithm. But you've followed some algorithm, so what was it? How did you sort things? Imagine I gave you a stack of papers. What do you do to sort them? Take a few minutes and think about it, talk amongst yourselves, and then we'll come back to this. If you're talking amongst yourselves, you're being too quiet. You don't have to whisper. All right, so what do you got? What did you do? I give you the stack of paper. What did you do? But what was the algorithm you did? That's the problem, sorting alphabetically. Okay, so how did you solve it?
First name or last name, I guess, was greater than the previous person would go ahead or behind, and you just build like a linear.
You're still just kind of explaining the problem. So what you're saying is you take something. I think what you're saying is basically insertion sort. I think that's what you're describing. Correct me if I'm wrong. Imagine I've got my unsorted collection here. I'm going to start with an empty collection here that's empty. And I take something out. I'm going to put it into the sorted collection where it belongs, right? I'm going to insert it where it belongs in the sorted collection. When it's the first one, I just put it there, great. Then I take the next one and I go, okay, does this go before or after the thing already in there? Before, okay, put it before. Take the next one, does this go before, between, or after? Is that what you're basically describing? Yeah, that's a common algorithm called insertion sort. You pick something and you insert it into a sorted collection where it belongs. Yeah. What else we got? There's one.
I personally probably have also done insertion sort, but I thought of another one.
I'm not sure what you're describing.
Okay, I'll try to explain, think about it for a bit, and I'll explain it later.
All right. What else we got? Don't tell me you don't know how to sort things. Uh-huh. Okay, so I break it down into a small component. How small?
I think it really just, I think it's kind of arbitrary. You can do it however small.
But how, okay, so I break it down into like a smaller pile. How do I sort that pile? I mean, that's the problem, is how do I sort it?
Are you thinking like you take like all the last names and do like all the A's and all the B's,
I guess.
and then like you look at the A's and go AA versus AB?
Yeah, so what that is, that's bucket sort. And bucket sort's actually great for something like this, where what you do is you just make I mean, it works for a general case, but if I'm sorting alphabetically, like a list of exams, let's say, this is what I would do, is I create a bucket, one for each letter, and then I put everyone whose names start with an A in the A bucket, and then B in the B bucket, and so on. And then when I'm done, I just put all the buckets in order. And that sorting algorithm is fantastic. But there's a catch in that, well, the bucket of A's isn't sorted. It's just a bunch of A's. But sometimes that's okay. Sometimes, like when I'm sorting by exams, the only reason I'm sorting alphabetically is so if someone wants to come have a look at it, it's easier for me to find them, right? I can just jump through, kind of like I'm looking through a phone book, right? More of a binary search to find somebody instead of just going through each one. Sure, the A's aren't sorted, but good enough. If your last name starts with an M and I'm in the M bucket, I can do a linear search on the M's pretty easily. I'm okay with that.
Okay, I feel kind of obligated to mention the best sort, obviously, where you take the pile of exams, you drop it on.
Yeah, that's BOGO sort. Take your exams, shuffle them. Are they in order? Yeah? Well, you're done. No? Well, shuffle them again. Are they in order? Who here thinks that's a good sort? Yeah, it's a terrible idea, but it's, it's a one way to sort something, I guess. What else do we got? Okay. So tell me something. Did you look up a bunch of sorting algorithms before today? Yes, yeah. That's what I thought. And so you're kind of ruining the spirit of what we're doing here, but I realize no one else is participating, which is pretty bad. Yeah, that's bubble sort. That's another common idea. And there's another common one I'd like to hit. What else? Does anyone else sort things differently? The fact that no one's raising their hand right now is pretty bad. It's the end of the semester. Give me a break. Why is it the other section? I had like 10 students up front being sorted in front of everybody, and you won't even raise your hand to tell me how you sort things. What's going on? Or do you just not know how to sort things? Did you all lie when you raised your hands that you sorted things? My 3-year-old can sort things. So the idea is, let's say I've got 2 piles. This is my unsorted group, and here's my sorted group. It starts empty. I do a linear search through this pile to find the smallest thing in this pile. I take it out, append it to the end of this list. It's empty, so it's the first thing in the list. Do it again. Do another scan, find the smallest thing remaining, because we just took the smallest thing out. So it'll be the next smallest thing, which is obviously, where would it go relative to the thing in this pile already? It'd be right after, right? You just append it to the end of that list. Yeah, exactly. Yeah, that's selection sort. So we hit insertion, bubble, but you cheated, and selection sort. And those are your 3 common ones. Chances are, if you've been sorting something, you've basically done one of those 3, if not a combination of them. Now, I have a question for you. When you were trying to describe your one about breaking it down, were you trying to describe one you found already?
Wasn't entirely sure how to describe what you're saying.
Gotcha. All right, so we're going to look at some of these algorithms. We're going to look at the code. And be warned that when we're looking at the code, it's not like linear search. At this point, if I showed you a linear search and you didn't immediately recognize it as a linear search, you're in trouble. Now, I'm about to show you an algorithm, and if you don't immediately understand what I'm showing you, you're normal. They're not overly complex, but they're definitely not trivial. They're not something you should look at and immediately understand. There's a bit to them. So don't worry if the code itself is a little overwhelming. Nothing in the code, no piece of the code should be overwhelming, but in aggregate, it might seem like a lot to chew on. But it's important to note that, for example, here is selection sort. What's important to note about selection sort is that's not selection sort. Selection sort is what he described. Selection sort is the idea of go find the smallest thing, put it over here. Go find the remaining smallest thing, add it to the end. Go find the next smallest thing, add it to the end. That's selection sort. That's the idea. This code is an implementation of selection sort, but it is not selection sort. No, the selection sort is that idea. Similarly with insertion sort. Insertion sort is the idea of you pick something and you insert it into the sorted collection where it belongs. And then bubble sort is the idea of if they're out of order, you swap them. Those three core ideas. Now, selection and insertion are actually remarkably similar, but one is absolutely worse than the other. I mean, they're both terrible, but one is worse. But here's like a little animation of selection sort. Here, it's not sorting it in two separate. It's sorting it in one list. Just swapping it where it belongs. Find the next smallest thing, swap. Next smallest, swap, right? It's not right or wrong to do it in the same list or separate lists or something. It doesn't matter. It's the underlying spirit of the algorithm, which is scan, find the smallest thing. Find the next smallest thing, the next smallest thing. That's selection sort. See? 5's the smallest, 6 is the smallest, 7's the smallest. So it scans, it finds the 0 because it's the smallest, puts it at the beginning. In this particular implementation, it swaps, right? So the 3 and the 6 get switched. This is just how this one is coded, or is actually implemented, I guess. But this is the idea of selection sort. Now, let's take a moment and think, how much work is this algorithm doing? Here I've got a list of size 10, but of course we want to think in general. I have a list of length n, right? And you figure, let's break the algorithm down into parts. Let's think about what's actually happening. Empty sorted list, unsorted list. I have to search through this unsorted list to find the smallest thing. You should be able to recognize that as an algorithm. What algorithm is that? Linear search. How much work is a linear search on a list of size n? N factorial. Absolutely not. Just n. I've got to go through and look at each thing. N factorial is like the worst of the worst. So I have to do, if I want to go scan this list to find the smallest thing in there, it's n units of work. I have the smallest thing, I put it into this sorted list. Am I done? No. All I did was find the first thing where it belongs. How many more things do I have left to sort? N minus 1. So I need to do another linear search. How many linear searches do I have to do? If after one linear search, one thing is where it belongs, how many linear searches do I have to do to put all n things where they belong? Well, that's how many remaining. I guess n minus 1 if you'd say, I don't know if you're thinking about what it is, but look, if I don't know if you don't understand. If you don't understand, I'm really concerned for you. I do one linear search, one thing is where it belongs. But I need n things to be where they belong. How many linear searches do I need to do? N. So if I have to do a linear search, how much work is a linear search? N. And I have to do that how many times? N. So if I have to do n units of work n times, how much work is that? N squared. I have to do n, and then another n, and then another n, and then another n. So I have to do I have to do n linear searches. And a linear search is n. But what are you going to say? Absolutely. So the point he brought up was, well, hold on. The first time I do a linear search, how many things are here? N. So it takes n units of work to search through it. But after I've done it once, how many things are left? N minus 1. So how much units of work is it to scan something that's n minus 1? N minus 1. Okay, I take another thing out. N minus 1 minus 1, n minus 2. So the next time, I have to do n minus 2. Look at n minus 2 things. So your point is, well, you said it's n units of work, n times, but really it's n units of work, then n minus 1 units of work, and then n minus 2 units of work, right? That's what you're saying. So let's go over here. Ah, don't look at this. Spoiler. So the first time, I have to do n units of work, right? The next time, I want to add up all the amount of work I have to do. I actually have to do only n minus 1 units of work. Right? And then the next time, it's actually n minus 2 units of work. Plus, and then obviously that list is going to approach the size of empty. So let's say like right? So how many things are here? How many individual things are being added together? N. It should be obvious, right? There's, 1 through n. Yeah.
So it's still considered a linear search even if there's only one thing left?
Well, let's think about this more generally. So your point of like how many scans are there? When you said there's n, I have to do n minus 1 scans, right? Where in reality, you're totally right, because after I scan this one, I don't really need to scan it anymore, right? There's only one thing there. I know it is what it is, right? But for simplicity here, let's just be like, oh, okay, go scan it. Well, there's only one thing there. But you're absolutely right. So when you said n minus 1, you were absolutely right, because that last thing, well, you didn't really need to. If there's 2 things left and I want to know which ones comes first, you pick it, and then you already know what's left. Does anyone recognize this, though? What does this look like to you? We've already talked about this like 2 months ago. Maybe it was 2 months ago. Or maybe I'm misremembering, but I'm pretty sure we talked about this. Nope. Nope. If I want to know, well, look, I want to know how much work is there done. I got to add all these things up together. So I want to add 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 all the way up to n, right? So I know why you're thinking recursion, right? I know where your head is, and like, okay, good, but that's not what I'm getting at right here. Yeah. Yeah. You all know this, you all recognize this. This is an arithmetic series, right? That equals that. Those are equal. Come on, we talked about this like 2 months ago. I know we did. I'm pretty sure we did. Come on, you all know this, right? Raise your hand if you've seen this before. 1 person has. 2 people, a couple of people, good. Now, look. I'm pretty sure you learned this in high school, but who here remember learning this in high school? 2 people? Okay, good. That's good. But for those of you that don't remember, it's because you had really bad math teachers in high school. I hate to tell you, you did. You may have loved them, they were terrible. Because if you don't remember this, it tells me that your math teacher did a really bad job teaching you. Because what a lot of math teachers do is they teach math as if it was handed down by the gods on stone tablets. And like, that equals that. Well, hold on, let me go back. That equals that. There, moving on, right? And then you spend like a day plugging numbers into this expression, and then suddenly you're supposed to know it now, right? That's how it's taught to you. That is terrible. Especially for programmers, because programmers, who here's kind of enjoyed programming a little bit, be honest? Yeah, it's kind of fun, right? Well, I got some, but who here kind of hates math? Yeah, I got bad news for you. Programming is just math. But we've tricked you into doing it. It seems like it's not math, but it's totally just math. I can tell you now, because it's the last day of the semester for us. But it is just math. But of course, it's not what you're used to, right? It's a different kind of math. And what I like about programming is, you start with these basic rules, and you kind of construct these rules together in a certain way. And if you follow all those rules, you get your result, right? So there's the systematic, we build the algorithms, we build the steps. So programmers are obsessed with building those steps. And when this was taught to me, I go, but what's the steps? How do I go from 1 plus 2 plus 3 plus blah, 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 to n times n plus 1 divided by 2? It's like, oh, there's a magic way to go from this to this. And if they never showed you why, they were terrible math teachers. If they never showed you how you get from that to that, they were really bad at their jobs and they should feel bad. Because it's actually not too bad. And it's actually, I'm willing to say, if they taught you how to go from that to that, you'd probably not forget it. If you remembered why. They told you what, but they didn't tell you why. And without knowing why, what's the motivation? At the end of the day, that math was not handed down by the gods on stone tablets. It was invented by some guy that was like, oh, look at this. And here you are writing programs, you're writing algorithms to do stuff. You're doing the same shit. This is perhaps far more general because it's an arithmetic series. But there's a way to go from this to that n times n plus 1 divided by 2, which seems weird. Like, what the hell is that? But here's the thing. I'm going to show you why. Now, n times n plus 1 divided by 2, there's a far more general form for any more general arithmetic series where you can be counting by certain numbers every time. This is a very specific version of an arithmetic series, but I'm going to show you, we can do the same derivation anyways, but this is if you're counting by ones to go to n. So here's how we get there. Here's what I'm going to do. For some weird reason, this is like the biggest catch, let's say. The biggest catch to me is we're just going to, now we don't have to do it this way, but what if, now let's see if we can kind of figure it out. What's this plus this? N plus 1, yeah, okay. So if I take that, I get n plus 1. And then you might also notice, what's this plus this? N plus 1. N minus 1 plus 2 is n plus 1, right? What's this plus this? N plus 1. That is pretty interesting, isn't it? N plus 1. So if I take the first thing and the last thing, it's n plus 1. If I take the second thing and the second last thing, it's n plus 1, right? Now, how many terms are there in total? Now, first of all, let me hit pause. Remember, we're adding these things up. It doesn't matter what order we add things in. 1 plus 2 plus 3 plus 4 is the same as 1 plus 5 plus 3. No. 1 plus 2 plus 3 plus 4 is the same thing as 1 plus 3 plus 2 plus 4, right? The order doesn't matter. We can add them up in whatever order we want. So how many terms are there in total? There's n. But of course, if I'm adding two things together at a time, right? Like, how many n plus 1s are there? Like half of them, right? If I said n plus 1, if I took this thing and this thing, took them out and added them together, then I took the remaining first thing and the last thing, n plus 1. So how many n plus 1s are there? Well, if there was n things in total, but like I took 2 at a time, well, now it's like n divided by 2 things. There's n divided by 2 n plus 1s. Okay, so what I'm saying is I have n plus 1 and how many n plus 1s do I have? N divided by 2. Yeah. That's how. That's why. So I'll re-explain it a slightly different way in case that didn't click. We're going to end up in the same place, so don't worry. I'm going to double this series. All right? I'm going to double it. I'm going to go n plus n minus 1 plus n minus 2 plus plus 3 plus 2 plus 1 plus n minus 1 plus n minus 2 plus blah, 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 plus 3 plus 2 plus 1. I'm going to do it twice. Right? But, you know, I'm running out of room. I'm not going to write it over here. I'm just going to write it under here. Right? So I just doubled it. So we got to remember that I doubled it, though. Remember, so if I double something, then I got to remember to undo that double. What do? Just divide it by 2, right? So we got to remember, we divide by 2 when we're done. All right. Well, hold on. It's the same shit as before. What happens if you add n and 1? n plus 1. What happens if you add n minus 1 plus 2? n plus 1. n minus 2 plus 3? n plus 1. How about 3 and n plus 2? Or n minus 2, pardon me. And yeah. So I actually have a whole bunch of n plus 1s here. But how many n plus 1s do I have? N, right? So I actually have n of them, right? I have n. Hold on, let me fix that. But of course, I doubled this series, so what do I have to do to undo it? Well, just divide it by 2. There, same idea, right? So that's the why. And chances are you'll have a harder time forgetting how to get what the arithmetic series expression is to do a quick calculation of it, like you were saying. You'll have a lot harder of a time forgetting that if you know why. This is all to say, so, and that's actually, 1/2 n squared plus n, right? That's the total amount of work that selection sort needs to do. Okay? That's the total amount of work. So if I gave you a list of size n, and I said to you, how much work is this doing? Well, that's your answer. But programmers are super lazy. And programmers are never, if I say like, how much work is that? A programmer will never tell you, oh, selection sort is 1/2 n squared plus, oh, actually, I messed up. This should be all like that, right? A programmer will never tell you that. Because what a programmer really cares about is, what's the dominant term? They want to know, like, they only care about, like, the worst part. When you look at that, if I were to plug in some value of n, which part is going to be responsible the most for how big the final number is? The squared part, right? When you square something, it gets way worse. So a programmer would say, oh, that's n squared. Selection sort's n squared. And then you go, well, really, it's actually n squared plus n divided by 2. A programmer would go like, it's n squared. It's n, that's all I care about. Programmers don't care about non-dominant terms. And they don't care about scales, like a scalar like that. They don't care about like a coefficient. They see this and go, oh, it's n squared. And to give you an idea of why this is interesting and important, we have, with a linear search, if I gave you a list of size n, how much work is it? N. If I double it, how much more work do you have to do? Twice as much work. But with something that's n squared, quadratic we would call this, and if you've always wondered why is square quadratic, what? It's because think of a square, right? It's 4 sides, that's all. To give you an idea of what this would mean, if I gave you a list of size n and told you to do selection sort, the total amount of work you have to do is n squared. If I doubled it, how much more work do you have to do? No, not 2n. 2n squared, which would be like 4 times the amount of work, right? What's 2 squared, right? So as n gets bigger, the amount of work this code has to do grows a hell of a lot faster than linear. I don't know if this will work really well. This is showing you, like only look at ignore the left-hand side there. If I doubled, here, these scales are all weird. How do I? There. Whoop, what did I do? There. If I gave you a list of size 10 and I said do a linear search, it would take 10 units of work. If I gave you a list of size 10 and told you to sort it with selection sort, it would be 100 units of work. The amount of work you have to do grows so much more rapidly with an n squared algorithm. If you have a linear algorithm, that's nothing. Quadratic, oof, Now it starts to get really bad. What I mean is, as your n gets bigger on the x-axis, the y-axis tells you how much more work you have to do. And you don't want to do more work. If I gave you 2 algorithms, now obviously comparing linear search and selection sort is not really fair because one's a search and one's a sort. But if I gave you an algorithm that was linear, or an algorithm to do the same thing that was quadratic, you'd take the linear one. The quadratic one just takes so much more time. And then, of course, you'd want something constant if it's possible. Or what was the relationship with binary search? Who remembers that? The quadratic is basically like a vertical line, right? Linear is whatever, it's linear, it's doing its thing. And look, compared to the linear, the log base 2 one almost looks like a horizontal line. If I gave you an algorithm that was log base 2 of n, or n squared, you take log base 2 of n. Compared to the linear, it almost looks constant. That almost looks like it doesn't even grow at all as n gets bigger. This is why it's important to have an idea of how much time these algorithms take and thinking about your algorithms. If you're lazy and you hit run, you might need to come back in a couple of years before your program will actually finish running. Any questions about any of that? All right.